The next question I have is from Njabulo Zalo, right? And it's actually a long question, but it's actually a very interesting question. Let's see what it says. So we have a mixture. Let me write it down. So we have a mixture. This one is a bit confusing just by mere looking at it because there's so many things that we have to do before we can actually start answering the question. A mixture of 0.2 moles of hydrogen chloride. Now another thing that the examiners will do, they'll just write hydrogen chloride and not actually give you the HCl. So make sure that you actually start practicing this. But all of this was actually what we did in grade 10. So you should be okay, matrix. And 0.11 moles of oxygen gas. Now remember, oxygen gas is a diatomic. There are 7 diatomics that you need to know. So oxygen gas will always be an O2, not just an O. O just means oxygen. So, and it is sealed. So it is sealed in a 200, now look at this one, centimeter 3 cubic centimeter flask. Already you must have sparks flying like da 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 da. That is something where they're trying to trick me at a certain temperature. At a certain temperature. And now, Njabula, I can see why this question might have given you a problem when you look at the memos, because probably maybe somewhere, somehow you forgot to add or to convert this. So now, remember, if I've got my volume and your volume is 200 cubic centimeters, to move it to cubic decimeters, you divide by 1,000. So my new volume will be 0.2 cubic decimeters, which will be dm minus 3. Let's see, that was the only thing that I needed to convert. Let's continue. So a mixture of 0.2 moles of hydrogen chloride, which is HCl, and 0.11 moles of oxygen gas, which is O2, it's diatomic, is sealed in a 0.2 cubic decimeter flask at a certain temperature. Now the question continues to say, it is found that, ooh, I see, Njabulo, it says 1.825 grams, and you're just like, no, but we always use moles. So Tops, what's going on? I'm going to show you how you do it. Of hydrogen chloride. So we have 1.825 grams of hydrogen chloride present at equilibrium. Remember, spelling doesn't count in physics, but let's not make those those mistakes. So now it's telling us we need to calculate the value of Kc. Now, another step that I've picked up, this thing is going to give us a bit of an issue. I'm going to show you 2 ways on how you can do it, Njabulo. The first one, you can say 1.825 grams of HCl. Now, then you tell yourself this is what we learned in grade 10. 1 mole of HCl is equivalent to how many grams of HCl? I'm going to work it out this side. HCl is a hydrogen bonded to a chlorine. If I look at my periodic table, or my molar mass for hydrogen is 1, plus that for chlorine is 35.5. When I add these two, I get 36.5, yes, 36.5 grams. So 1 mole of HCl is equivalent to 36.5. So now, if you're still struggling with your periodic table a little bit, just go ahead, look at it, and practice. Let's see what I get here. If I put these on a calculator. So now let's calculate the moles. So how do I know I've got moles? Moles of this one, the moles of HCl will cancel, the grams of HCl rather will cancel the grams of HCl. I'm only left with the moles of HCl. And then let's calculate that. So at the top, remember this is over a 1. Let me do it like this. So at the top, I've got 1.825, close my bracket. At the bottom, I've got 36.5, close my bracket. And then I end up with 0.05. And that is moles, 0.05 moles of HCl. So at equilibrium, we have 0.05 moles of HCl. So this was a little bit tricky, but now let's see what they actually want us to establish. So now I see Njabula has also given us an equation, and Njabula's equation says I've got 4 HCl in grams. I've got my oxygen gas, which is also in grams. It's equilibrium. I hope I'm going to have space here. I've got 2Cl2 and I've got 2H2O. So now we use my method or the method, depending what your teacher uses. I like, let me use a different color. Let's use green. This is what I start with, this is what I've used, and this is what I had at equilibrium. So according to Njabula's question, a mixture of 0.2 moles of hydrochloric acid. So initially, we start off with 0.2 moles of hydrochloric acid and 0.11 moles of oxygen gas. So I've got 0.11 moles of hydrogen gas. Remember, if this is what we start with, meaning we don't have products yet, so this will be 0 moles, and this will also then be 0 moles. And it continues to tell us it's in a flask, which we've converted. It is found is spelled very wrong to be like, it's found that now we converted the 1.825 grams of hydrogen chloride into moles. So at equilibrium, we have 0.05 moles of HCl. This is at equilibrium, which I'm going to have 0.05 moles. Then I'm going to do the same thing. Looking at my mole ratios, it's a ratio of 4 is to 1 is to 2 is to 2. So what does that mean, Tobile? Remember, this is what you started off with. All of a sudden at the end, you had 0.05. So you can say 0.2 minus 0.05 gives me, how many x's do I have there? I'm going to have 4 x's here. I'm going to have 1 x there. I've got 2 x's there, and I've got 2 x's there. Where did I get my x's? The mole ratios. So it's equal to 4x because I don't know how much was used up. Now let's calculate what I get here. I want to calculate this too. So if I've got 0.2 and I subtract 0.05, I get 0.15. I'm going to get 0.15 is equal to 4x. Now, I want x by itself. You divide both sides with the number that's irritating the x. In this case, it is 4. This and this will cancel. Let's find our value of x. Let's calculate that. So I'm going to have 0.15 divided by 4 because I only want the value of 1x. So x will be 0, oh, I didn't catch that number. It will be 0.0375. So my x will be 0.0375. Now I want us to think, my darlings, if the value of 1x is 0.0375, I have 4 x's on this side. So I'm going to take the value of 1x, multiply that by 4. I get 0.15. So I'm going to erase this because now I know what my value is. I'm going to get 0.15. I've got the value of 1x. It's the one I just worked out. Value of 1x is 0.0375. Now I've got value of 2 x's. I'm going to take this number, the 0.0375, times that by 2. Let's go to my calculator. So I'm going to have 0.0375, multiply that by 2, gives me the value because I had a 2x because of the mole ratio. I'm going to get 0.075. I think I caught that. And again, for 2 x's on this side, it's going to be the same because the mole ratio is the same, which I'm also going to have 0.075. Now, I want us to think. If I've started off with these ones, they are getting less and less and less. So that's why these are getting less. So 0.2 minus 0.15 will give me the 0.05. And now we need to subtract these two because they are being used up. So I'm going to say 0.11. I'm doing this one now. I'm using it up, and well, how much did I use up? 0.0375. I'm going to end up with very big number. So I've got, yes, I think I've got it. I'm going to have 0.0725. And for the mole ratio of 2, let's calculate that one. So this one, so no, we actually don't have to calculate this one because I started off with 0, I've gained, and I've gained. So this will be the same, 0.75. I'm going to have 0.075 because the mole ratios are the same. I'm going to remove this. Oh, they taught me a trick on how to do that. Voila. So now this is what I have at equilibrium. How did you get this tops? Initially I had 0.2 moles and I had 0.11. These two were 0, right? At equilibrium, they told me I have 1.825 grams, which I converted to moles, which is how I got that. Then I said 0.2 subtracted by this, and then I solved my x with my ratio. That's how I got all the others, but I'm not done. I need to calculate my Kc. Now, concentration is N over V. My moles at equilibrium, I've got 0.05. Now, they've told us that the floss was 200 cubic centimeters. If you do not convert the 200 cubic centimeters to cubic decimeters, unfortunately, you're going to lose marks and you might even face some negative marking. So let's not do that. So I'm going to use the 0.2. On this side, I've got C is equal to N over V. I've got 0.0725 all over 0.2. C is equal to N over V. 0.075 all over 0.2. C will give me N over V, 0.075, just say all over 0.2 so that you can see. Now let's work it out to what we actually have. Start with the first one. I'm going to start with this side. I've got 0.05 divided by, it's in a flask of 0.2 cubic decimeters. So I get 0.25, I get 0.25. Remember, when you're calculating concentration, it's mole cubic decimeter. Now, if you're writing it on paper, you're obviously going to have more space. So make sure that it just looks nice and neat and your examiners see everything. We're going to do oxygen gas now. Let's start again. I've got 0.0725 divided by 0.2. I get a very long number. Remember, you can round it off now or only at the end. I actually prefer rounding it off at the end. It becomes more accurate. So I get 0.3625 if I caught it correctly. And that is mole per cubic decimeter. Let's do the last one. Those are exactly the same. So that's going to be a little bit less simpler. 0.075 divided by, it is in a container, which is 0.2 cubic decimeters. I get 0.375. So here I get 0.375. So this will be exactly the same because of the mole ratios. This is mole per cubic decimeter, and this will also be mole per cubic decimeter. However, we are not done. When we calculate the Kc, we need to find the concentration of each in equilibrium. We found this concentration, so this is what we are then going to use. Now, let me actually use another color. Let's use a different color. I'm going to work here. When you're calculating for the Kc, we have our products. We have them over our reactants. Products are on your right-hand side. Reactants are on your left-hand side. When we're calculating Kc, if we have any liquids or any solids, we don't include them. So all of this is gases. Any solids, any liquids, we don't include them. They're inconsistent. We only do gases and aqueous solutions. So now let's see. I now have to look at this reaction here. So my product is on this side. So I'm going to have Cl2. I think I'll remember it. Cl2, remember, the number in front becomes an exponent. And then I'm going to have H2O. It also has a mole ratio of 2, and the number in front becomes an exponent. All over my reactants. The reactants that I have, I've got HCl. Now, it has a mole ratio of 4, and that becomes an exponent. I've got oxygen gas, which only has 1. You don't have to write it. Now, let's see. For my Cl, I have at equilibrium, remember, we have 0.3625 to the exponent 2. I've got 0.3625 to the exponent 2 for my water. Because of the mole ratios, they are the same. I'm going to get 0.25 to the exponent 4. And my oxygen gas, I'm going to get 0.3625 to the exponent 1. You don't really have to write it. So let's calculate this and see what our value for Kc is. Put everything in a bracket, 0.3625, close bracket, exponent 2. I've got 0.3625, close bracket, exponent 2. Take that down. I'm going to get 0.25 to the exponent 4. I think that one I put a, yeah, there we are. I've got 0.3625. Exponent 1, you don't have to write it. Anything to the exponent 1 will give you that exponent. Let me just see if I've got everything there. I get 12 here. Hope I've calculated everything well. I get 12.19. If the 4 doesn't change the 9, so we can just leave it as 12.19. Remember that Kc does not have a value. Let's just go through everything again. What we first did, I think in Jabulo Zalo, the biggest thing or the biggest challenge, I think, for this question would have been to convert the volume to cubic decimeters, and for the fact that they've given you 8.25 was actually a problem. But I understand why an examiner would actually give you such a question, because before this we've done stoichiometry, and we've done a lot of stoichiometry in grade 11 where we have to move to moles and grams and so forth and one molecule to the next. So they just want to spice things up and see if can you now work with stoichiometry while working with chemical equilibrium to then get to your final answer. So just by mere looking at this part, all of this part is stoichiometry. Then you get a lot of mathematics on this table. Then this becomes chemistry then again. And then when we have to calculate Kc, it's then a little bit more chemistry. So, I mean, a question like this, it was going for 9 marks. So you can imagine you had to get a mark for converting this. You had to get a mark for converting this using the correct ratios and actually showing how you got the 36.5. Remember, I've already erased that. And then again, using the correct ratios in the system, and then to find the correct values for the C equals N over V. But otherwise, this is then how I would have answered this question for Njabulo. And Njabulo, thank you so much for your question. It's actually a brilliant question. Very good practice questions, guys. Always make sure that you see the nitty-gritties that these examiners are trying to do. And trust and believe me, everything you see on a question paper is something that you've already done or seen before.